Okay. So in the last class, we had sufficiently motivated regression and discussed what is really linear about linear regression. And we'll build upon that further today. So we built up our notation. So you have this data set consisting of m examples, and each instance is a tuple. The input x, which is a set of independent variables, and the output, which are the target dependent variables. Now, each of this xj, yj is such that xj is a vector and yj is just a scalar to begin with. So, we'll later probably consider more complex settings where yj itself could be complex, specifically the case of graphical models, Bayesian networks. But here, each yj is a scalar, and more specifically, it's a real. So this was our canonical running example where an advertiser, kind of a company wants to advertise to TV, and it's measuring the investment on TV ads vis-a-vis the output, which is the amount of sales. And we said that the advertisement itself could have complex functions associated with it. So instead of just talking about the revenue associated, the amount of money associated with an investment for an ad, we could have phi 1 to phi p, and these are functions. These are called basis functions. Just to recap, we could say that phi 1 is the time duration of the ad, phi 2 is the money invested into the ad, phi 3 could be the time of the day of the ad, and so on. The output, individual outputs y1 to ym, in general yj is a scalar, as I said, and this could be the sale for jth ad or jth object. W is a vector associated with the basis functions. So in general, you could have wi is weight or importance of the ith basis function phi I. Let me use j here. Wj is the weight or importance of phi j. Is this clear? So under these settings, you had derived one possible objective that we might be interested in minimizing to obtain W star, the desirable parameter vector, and that corresponds to the point that minimizes, the parameter configuration that minimizes an error function which is a function of W, the parameter vector, and the data set D, which we showed in the previous slide. Now more specifically, this error function that we had identified as one of potential interest was the sum of square error, and we had derived this to be phi W minus y L2 norm squared, where the w, y and phi, capital phi, are exactly as shown on the slide. So we have gone this far. Now the general regression problem is that instead of w star, you are interested in f star, right? What happened in our specific case is our f was parameterized by w, fx comma w, we assume to be the linear regression model, w transpose phi x. But you could just replace this w star with a more general f star, which you obtained by minimizing the error function e ef comma d with respect to the search space of f. That's the more general problem setting. We are looking at the more specific one, the general regression problem. And what we are doing is we are parameterizing the regression problem. And what does parameterization mean? Meaning that f is now considered a function of w, and you're finding the w that minimizes the error function. So you're kind of constraining the search space of f. In general, this f could be all polynomials. I mean, it could be anything. In fact, you could say all function classes or the entire space of functions. Here we're saying only linear functions, and this is one way you put constraint. Right? You are optimizing over the parameter space of that constrained space of functions. So, just to bring a closure to this discussion, what we are doing here in the parameterized form is this calligraphic f. That class is now becoming the space of functions with different values of w, where this f might have a more specific form. So what we are interested in right now is linear, but it could also be polynomial, it could be trigonometric forms, and so on. So for example, if you do a basic, I would say, some course on wavelet transforms or Fourier, how many of you are familiar with the Fourier series? So you could assume functional forms in terms of the Fourier basis or the wavelet basis. The basis phi, this basis phi could be the Fourier basis, could be the wavelet basis. For purposes of this course, we will assume that phi is given to you. To begin with, we will assume phi is given to you. We will also see ways by which phi could be learned implicitly. Okay, so okay, let's continue our discussion now on the specific form we discussed in the last class, the linear regression problem. And this is exactly what I have written on the board. We want to find this w star. Okay. How do you solve for this? How do you solve this least square? Basically, optimal point. Any ideas? Yes. You look at either this form or the form written on the board. How do you obtain a closed form for this? So there exists a closed form. Some of you feel that. Have you ever solved this before? Yes. Can you solve this in the one-dimensional case where you're only dealing with, say, the phi 1 and maybe a phi 0, which corresponds to the bias term? So let's consider the closed form solution for the 1D data. Okay. The simplest case basically where phi 1 xi is nothing but just xi itself, and phi 0 xi is 1. Okay, so you'll have the corresponding weights W0 corresponding to phi 0 and W1 corresponding to phi. Right? So let's try and solve this. You all know that you could minimize this by setting the partial derivatives to 0. So why don't we solve this? Is this correct? Yeah, minus 0. So you can work these out further. What will be the form of W0? Okay, what was W1? Summation of xi upon n into. Okay. So can you write it in terms of averages? So xi upon n. Some of you are getting those terms, right? Phi I upon n. So let's make this shorthand. We'll assume that x bar is summation xi divided by n. Y bar is the average. So anyone can help me work out the details further in terms of x bar and y bar. X square bar. But you can manage without that just by a little bit of expansion. So avoid x square bar and all that. And try and survive with this simple average. Okay, so anyone wants to dictate a possible solution? So that is what? That's the expression for W1. W1 is x bar No, sorry, x bar, y bar, x square bar. Okay, you cannot avoid this. This is what you get for W1. Sorry, x. Okay, so and W0. So W0 you're able to derive in terms of W1. Okay, so I put a question mark around these, but you should get something like this. So yes, some of that you have got correct. You got this x bar, y bar. I think there's a little bit of a problem with the scale. Pardon? Yeah, so there's this divided by n, xi, yi divided by n. And you can avoid taking the average of x square by a little bit of expansion. So, so you can verify that this is the solution you get. I'm not get into details right now. This is W0, this is W1 stuff. So you could just further verify that W1 is nothing but, W1 star is nothing but some scale version of the correlation, right? I mean the correlation coefficient between x1 and two random variables x and y would be expressed in terms of x minus x bar and y minus y bar, right? It's suitably normalized, and that's what W1 is. So W1 kind of roughly corresponds to a linear correlation coefficient. Okay, I should remind you that in this specific simple example, we assume that phi1 xi is nothing but just xi, where xi itself was just a scalar real, and phi0 xi was 1. In the simple setting, this is all assuming the phi's were basically the original points were not complex, they were just simple scalar. But as pointed out, in general, we'll have to deal with complex x, and you have to design basis functions on those complex x's. Okay, so this is a closed form expression. Doesn't look far from where most of you are. So I would request that you verify the homework. So now let's try and do this in general for p-dimensional data. By what we mean by p-dimensional data is that we have p basis functions, and we can assume that one of them, let's say phi p xi, could be a 1. One of them could be basically to factor in the bias term. But we'll not bother ourselves with that again and again. The needful will be done. So with this, our yi is this linear function. And now I have this w star which I need to obtain. Going back to the more general setting. So now how do you solve? There are two ways to write this. One on the board, one on the slide. Okay. So Everyone understood how partial derivatives are computed, right? For that simple example. Anyone who couldn't follow the previous slide? And an honest show of hands. The derivation of W0, W1 for the simple case. Is there anyone who could not follow? So if you could follow that, what would you state more generally? What would you require in this setting? What would be required of W star? Yes. So let's write down the necessary condition. So this is actually necessary condition of optimality. So what would you require? The partial derivative of the error function with respect to W1 at W star should be 0. So should be the partial derivative of the error function with respect to W2 and so on until WP. Now if you stack these partial derivatives in a vector, one on top of the other, you get something called the gradient vector. So the gradient vector of the error function with respect to W evaluated at W star, where the error function is a function of W and D, is a vector of partial derivatives of E with respect to W1 evaluated at W star, of E with respect to W2 evaluated at W star, and so on. It's called the gradient vector. What do you understand by gradients in general? Slope. So you come from the hillside, or you come from the hillside, or you climb the small hillock going to the sack, right, from the institute area. So you climb down. So the gradient, you say there's a negative gradient when you climb down, there's a positive gradient when you climb up, right? So this is the rate of change. When things are increasing, you say, well, it's positive gradient. When it's decreasing, there's a negative gradient. The only difference is that there we generally talk about gradient in a fixed direction. We have the direction in our mind. This is talking about the direction as well as the magnitude. If you want to know purely only the gradient magnitude, you could talk of the directional derivative, but we'll not get into it. I have posted more detailed notes on optimization if you want or are interested. But for the time being, this gradient has both the magnitude and direction of rate of increase of a function, right? And this is nothing but a vector of partial derivatives. So if you had a function E plotted in terms of multiple parameters W1 to WP, now E would have some shape. The gradient vector at some point, as I said, talks about both the magnitude and direction. So it gives you an indication of in which direction you should move. The gradient vector is completely in this plane, right? So it's telling you in which direction you should move so that the function increases by the maximum amount. in which direction you should move. So this is basically the gradient direction. Exactly. But if you want more geometric understanding, you can go through my notes. I've also CDeep also has video record in my convex optimization course in the last offering. I can point you to that, and that will give you an idea of why all this exists. But broadly, all we are interested in right now is that there exists a vector like gradient, which is in the space of all the w's. So it's a p-dimensional vector. There are p w's, and this gradient is a p-dimensional vector, which means it must lie in this plane, spanned by all the w's. And that vector is exactly the direction in which if you move, you'll have maximum rate of increase of this function e. And what we are insisting on here is that if the function has a minimum at w star, then there should be no direction in which you are able to increase locally. Locally, it's the minimum. Okay. So what we expect is at this point, point of minimum. The point of minimum, you would expect the gradient of e with respect to w to be 0. That's all we are going to use, and that's what you used in the two-dimensional case. The previous slide, p was 2 and we derived w1 star and w0 star using this idea. So this condition, it's not idea, it's condition, it's a necessary condition. You can prove that this is a necessary condition. And if it's convex function, it's also subject to certain topological conditions. It's also a sufficient condition. Okay, so this is necessary condition, necessary and sufficient for most purposes. A convex function is basically a function which is cup shaped. That's again suffices. Is this convex function? This is a concave function, and you could have functions which are neither concave nor convex. Function like this is convex in some regions, concave in some regions, and probably neither convex nor concave in some other regions. This is all you need right now. So how do you set the gradient to 0? And how do you compute the w star where the gradient becomes 0? Okay, so I'll again introduce you to some simple tricks, because gradient computation is going to be important for you in this course. Whether you understand the theory behind it or not, you should at least be able to compute gradients. Okay, so I'm kind of giving you the final answer. Can you work backwards? So here's the objective. You can write again this objective in terms of norms. Oh, not the objective. So this is the gradient we want to compute. And we want the gradient to go to 0 at w star. Phi w minus y norm 2 norm square. Can you write it differently? This is equal to, can I write this? Yeah. So a vector x transpose x, v transpose v, vector v transpose v is the same as 2 norm square. Using this, phi w minus y transpose. Now you can expand this vector dot product, right? So the transpose distributes across all the components of the vector. across all the components of the arithmetic expression. There's an algebraic expression. There's an algebraic expression. So I'll have gradient of the transpose of this component, the transpose of this component times these two components. Now, what do you know about partial derivatives of sums? Partial derivative of a sum is the sum of the partial derivatives. So I could do the same thing with gradient. I'll distribute the gradient across all these four components. And that leads to the gradient with respect to W. Now the first component I could further expand. Yeah, I'm going to use the board for important concepts. So what is AV transpose? Is it written as V transpose? A transpose. So I could do the same thing here. The first component will be W transpose, phi W, right? Minus the second component W transpose phi transpose Y minus the gradient of this is phi transpose phi W plus the gradient with respect to W of Y transpose Y. So I'm just going to color code these different components. What happens to this last component, gradient with respect to W of Y transpose Y? This disappears, 0. What about the other four? Okay, now you can, again we will not get into details, but I'll give you some tricks. So if you have the gradient with respect to W of W transpose something, which is a quadratic expression which also ends in W. So this will just be 2 times phi transpose phi W. And this is very similar to your quadratic expressions. Think of W as a scalar. W into phi square into W square phi, right? And that would the partial derivative with respect to W would be 2 times phi W. So it's similar to that. So this would be the gradient would evaluate to phi transpose phi W. Sorry, 2 times. 2 times phi transpose phi W. Like quadratic expressions. Okay, gradient with respect to V of V transpose AV is 2AV. It's like these VAV. Think of this as partial derivative with respect to V of VAV, just 2AV. So this component, again, this is straightforward. You could actually write it down, and you realize that this gradient is nothing but just phi transpose Y. The W transpose sitting at the front will vanish. The third component. So to get the third component, you first realize that y transpose phi w and w transpose phi transpose y are exactly the same. Why? They transpose each other. Okay, so the scalar, right? So w transpose phi transpose y. In fact, the entire expression is a scalar. This entire expression was originally a scalar. So w transpose phi transpose y, which is scalar, will therefore equal to its transpose. W transpose phi transpose y transpose. Scalar transpose is equal to scalar, and that is nothing but, again, now you just distribute the transpose and multiply them in the inverse sequence. Y transpose phi, sorry, yeah, I had to do the other way. Okay, anyways, doesn't matter. So you see that this y transpose phi w is nothing but the transpose of the other thing, right? So I could also show you the other way. I can take the transpose of this and then do the gradient, and that will again distribute w transpose phi transpose y, its gradient with respect to w, and I immediately notice that this is the same expression here. Oh, there's a negative sign here. That's the only difference. This there also is a negative. Negative here. Both are negative. So minus phi transpose phi happens to be the gradient of both the components. So yeah, good question. So let's for the time being assume that I just presented the final solution. We are not there as yet. Right? Let's go step at a time. So this so far is clear. Okay, so what do we have finally? The gradient is 2 phi transpose phi w minus phi transpose y minus phi transpose y. So this gradient vector for the least squares case is 2 phi transpose phi w minus phi transpose y. Right, and this should be 0 at the point of optimality. So at w star this should be 0. Right, then you can easily work out that w star must be again phi transpose phi, this component whole inverse phi transpose y. Now somebody asked this question, invertibility. So I'll try to play safe and say, well, the actual solution we are seeking is that phi transpose phi w equals phi transpose y. That's all we can say. We have moved one step ahead, assuming invertibility of phi transpose y. Is clear? V transpose AV, yes. Yes. But by design, phi transpose phi will always be symmetric. Phi transpose phi, I mean, we didn't use that explicitly, but it's kind of something that occurs there. So phi transpose phi, any matrix transposed into the matrix will always be symmetric. In fact, it will not be just symmetric, it will also be positive, semi-definite. So I want to make sure everyone understands this, the spirit behind this derivation. The fact that gradient distributes itself, the fact that we have used some matrix operations involving transposes. Okay, so is this clear? So this is a solution account of convexity and differentiability of E. See optional reading notes on convex optimization. Again, some of this you have to trust me and read up if you need to convince yourself. Now, do you really require all this ammunition for least squares? Turns out there's a very simple way to derive this closed form solution using geometrical intuition, and let's just understand that quickly. Okay, I think geometrical intuition is very important, as important as the math, heavy machinery. Okay, so for a moment, we'll assume that we are back to this problem. We need to minimize, and let's say we didn't really want the gradient machinery. How many of you didn't like gradient? Some of you didn't like. So I'll make you happy and just erase the gradient vector, but it will come back. I can't keep you happy for too long. So I'm going to show how this can be derived using simple geometrical intuition. Okay, and it's basically based on this idea of column space. So if 0 is attained at W star, let's say the W star where you seek the minimum, the error actually is 0. Okay, so we'll consider two cases. If error is 0 at W star, minimize it and actually make it 0. Obviously, it cannot be negative. Then what can I say? I can say that if the norm is going to go to 0, then the vector must also be 0. Right? That's a property of norm. A norm is 0 if and only if the vector is 0. Phi W star will therefore equal y. Okay? That's exactly we have said here. It has a solution if y is in the column space, the subspace of Rm followed by the column vectors of phi. So, what do you mean by the column vectors? For those who are familiar, fine, but we are basically referring to these vectors. These are the column vectors. And linear combinations of those column vectors is the column space. So, we are saying that y must belong to the column space of phi if there exists a W star for which the error becomes 0. Is that clear? So, how do you visualize this? So, this is how we visualize it. Here's my y is the same as y star. Okay, so if y was here, actually, if y was indeed here, right, in the column space, then W star could be found. But what if y is not in the column space? Y is not in the column space of phi, which means y doesn't belong to this column space. Well, there may be a y star that belongs to the column space, some other point y star. Okay, so we are now continuing this case. We are saying, well, if EW star D is not equal to 0, that is y is not in the column space of phi, then there exists some y star which is in the column space. There are many, of course, the column space is non-empty as of now. We are not dealing with, well, I mean, it will not be, it will never be empty. Even if phi is a 0 vector, rank 1 matrix, will have something like that, 0 vector at least. Okay, so consider y star in the column space of phi, and that's the y star we are talking about. Okay, I want you to pause and think. Are we interested in any y star? There's a lot in the figure already. So I want everyone to think. Some of you suggesting that the y star should be such that a perpendicular, the line joining y, which I am trying to fit with y star, should be perpendicular to the column space. Does that make sense? I mean, what would this minimization do? It say I want phi w minus y to be minimum. But now I am saying y star is in the column space, which means that y star is basically phi w. Replace phi w with y star. What do I want? Y star to be closest to y. If y star should be closest to y, then certainly y star cannot be here. If y star is not, if y star is here, what will happen? You have to traverse a more distance. You have to walk more to get to y, and that's something you don't want to afford. Likewise, y star cannot be here, right? So y star, because if you move, I mean, the shortest distance from a point to a plane will be based on the perpendicular. Is it clear to everyone? So now let's write down what this means. Okay, so I want everyone to write down what will this mean. And I'll work with you. So phi w star should be equal to y star, because y star is what lies on the, and then what we also want is y minus y star should be perpendicular to column space of phi, or just say perpendicular to phi itself, perpendicular to every vector in phi, perpendicular to all linear combinations of phi. They are related, right? So are these two statements okay? You can also say y minus y star should be perpendicular to the column space, but it suffices. If it is perpendicular to phi, you are done, and it's perpendicular to any linear combination of the columns of phi. Everyone with me? Okay, so now how do you solve this? Now I want you to work out the rest of the details. And the hint is you will get the same solution. These two should give you the solution. Everybody follow? I'm happy if some questions are coming up. Please ask questions. And there's no question that is actually silly or trivial. Please ask. Okay. Okay. So the dimensions of y minus y star, the and the dimension of a single column of phi are exactly the same. In terms of dimensions, y has m components, and a column of phi has exactly m components. So it might help to just see that y minus y star will be also m dimension. Actually, y minus y star transpose. Y minus y star is a column vector. By default, any vector is a column vector. So y minus y star is a row vector. And what are we requiring? That this is orthogonal to every column of phi. So I might as well say that y minus y star transpose phi is equal to 0. That's the whole point. Okay, so these two conditions I'm now going to again write. So the y minus y star orthogonal to phi is the same as saying y minus y star transpose column 1 of phi is 0, y minus y star transpose column 2 of phi is 0, and so on, right? So I might as well write y minus y star transpose the entire matrix phi equals 0, because this operation is going to take the dot product with every column of phi and make each of them 0. This is a vector inequality, plus the other requirement, which is phi w star, let's not say plus, and this other requirement, that phi w star equal to y star. What would these two mean? Now I should be able to solve. Yeah. So y star is phi w star. So you substitute it here. Substitute for y star as phi w star here, and that will give you y minus phi w star transpose phi equals 0, and that means that phi transpose, so w star, I could take it the other way also, that may be easier. I can do a transpose again, but I mean it doesn't matter whether you're here or there. You could just take the transpose the other way, phi transpose y minus phi w star equals 0, right? And that will give you w star phi transpose phi equals phi transpose. So overall you'll get this. And again, you could, if you assume invertibility of phi transpose phi, then you get w star is phi transpose phi inverse phi transpose phi. The same expression where we began, using gradients. Is this clear to everyone? Okay, so this is summarized here. These steps you already got, and then we substitute. All we are doing is substituting for this expression here in y star or here, either ways, and that gives you exactly what we set out to show. So this is our final expression. Now, some of you were wondering why phi transpose phi has been inverted. Is it invertible? So here's an interesting observation, that phi transpose phi is invertible if and only if phi has full column rank. Can you prove this? What does this mean? Before proving this, what does this mean? What does full column rank of phi mean? Yeah, but what does it mean to say all columns are independent? What is phi? The phi was what? It was basically feature 1 on all examples, feature 2 on all examples. stacked on one on top of another. So they basically are feature vectors across a single feature across all examples. So feature 1 on all examples, feature 2 on all examples, feature P on all examples. That's what phi was, right? So what does it mean that phi has full column rank then? So every feature is basically doing something useful. No feature is just a combination of other features. Now, is that in general desirable? That is desirable. There's no point putting the same feature 3 times. Of course, we'll later discuss techniques in which you may do that for some other purposes. But let's assume that this doesn't make sense for starters. So this makes so basically phi should have full column rank to make meaningful use of the features. So all you need is the features to be linearly independent. Okay, and then in this case, phi transpose phi is invertible. So it's a fair thing to ask for, and then you can get invertibility of phi transpose phi. Okay, so now you can prove that it is if phi is full column rank, then phi transpose phi is invertible, and here's the proof. So suppose we assume phi has full column rank. I am not going to write the proof; it's all here, written here already. So if phi has full column rank, then what it means is, okay, I made a small mistake here. Yeah, okay. So I just have to say, suppose there exists. That's what I mean. Okay, we assume that phi has full column rank. Suppose there exists a W such that phi transpose phi W equal to 0, which means that phi transpose phi is not invertible, right? If phi transpose phi is not invertible, then you would have some non-trivial null space. So if this exists, then what happens? You pre-multiply by W, but W transpose phi W should also be equal to 0, even though W exists. In fact, I could also further say that if it were linearly, if it were not invertible, then W can be non-zero. But let's say for the time being there exists some W, it may be 0 or non-zero. So pre-multiplying by W transpose, a 0 expression will remain 0. And now I just W transpose phi transpose, I express it as phi W transpose, something we have been doing. So phi W transpose phi W 0, and again one more step here. This phi W transpose phi W is nothing but phi W norm 2 norm square. If 2 norm square of a vector is 0, then the vector must be 0. Now if phi W is 0, now we are unhappy with this. We said that phi has full column rank. Okay. Phi has full column rank, and now we are saying phi W equal to 0. What should that mean? That the only linear combination of linearly independent vectors that will give you 0 is 0, right? So these two together mean that these two together mean that W must be 0. Phi W equals 0 and phi is full column rank, which means W equals 0. So hence phi transpose phi is invertible if phi is full column rank. Is that clear? You can also prove it the other way. Phi transpose phi is invertible. If phi transpose phi is invertible, then phi must have full column rank. Right? You are proving it the other way. So let's say phi transpose phi is invertible, and suppose phi W were 0. Right? If phi W were 0 and phi transpose phi is invertible, then phi transpose phi W will also be equal to 0. But then these two, the fact that phi transpose phi is invertible and phi transpose phi w equals 0 will imply that w equals 0. Why? Because if phi transpose phi is invertible, it will have full column rank. In fact, row rank should be equal to column rank, should be equal to the dimension. Okay, so these two conditions, invertibility and phi transpose phi equals 0, mean that w equals 0, which means that phi has full column rank. So if phi w equal to 0, w must be 0, which means phi has full column rank. So this, so you've seen proofs both ways, right? So again, this is following from simple linear algebra. Probably you have done this before. Okay, so the summary is that if phi has linearly independent features, phi transpose phi is invertible, you can actually go ahead and solve for w star exactly. If not, you can go back to your previous expression, phi transpose phi w star equals phi transpose y. And what did you do in your lab 1? You wrote what? You wrote Gauss elimination, didn't you? I mean, you are part of that was RREF and all that. So solve. In fact, you do that even if it were into invertible. Okay, so here's the summary. This linear regression we discussed, but it is not naively linear. And there's good machinery behind it. And linear regression is linear in W, but not in X. Okay, it's linear in the W. It's also linear in phi's. But in X, it could be arbitrarily nonlinear. So what we'll do in the next class, I'll show you how you can build polynomial functions of X by taking phi to be basically different polynomial terms. Right? So we'll do that in the next class. But this linear regression is not naively linear, and this is important message to go. And we'll continue in the next class. We talk about you can actually generalize regression to ridge regression, which is a form of regression with a modification to the error function, and then logistic regression, which is meant for classification, which we'll see a couple of classes later. What we'll do in the next class is specifically related to linear regression again. We'll say, is there a probabilistic interpretation for linear regression? So this probability will actually give us a lot more tools to understand linear regression, and we'll also discuss if there are efficient optimization algorithms. We'll be back to gradient. So whether you like gradients or not, they are going to come and haunt you. So please make friends with gradients in the next few days.